In the last video, we finished off with the introduction of the tuned mass damper that functions as a neutralizer of the high wind and severe earthquake. This week, we will look more deeply regarding earthquakes, seismic issues that Taipei 101 had to consider while on construction. Do you remember where we can find Taipei 101? I have mentioned that Taipei 101 is in the upper side of Taiwan, near a river. Its location is also where the earthquakes occur often. Raising a tallest building at that time in that kind of dangerous area was a challenge. As you can see here, 4 fault lines, a belt that seismics occur often, were closely located. Taipei Fault, Kangzhou Fault, Shanchao Fault, and Huishinchang Fault. Among those, Shanchao and Huishinchang fault lines were the major ones, usually causing micro-earthquakes which were less than magnitude 2 before the construction of Taipei 101. Interesting things happened after the construction had started. The magnitude of the earthquakes started to go over level 2. The start was the one that occurred in 2002, during the construction. It destroyed the crane as a result. Many started to wonder if the increase of the magnitude of the earthquake is due to Taipei 101, considering the weight of the building. Geologist Cheng Honglin once mentioned about this. He suggested that the stress from the skyscraper may have reopened an ancient earthquake fault, since after the construction was finished, 2 larger earthquakes, magnitude 3.8 and 3.2 directly beneath Taipei 101, which were big enough to feel, occurred. On the other side, there was John Vidal, an earthquake expert, who stood against that suggestion. John mentioned that a building will change the stress on the ground below, but this will not be enough to reach the level where earthquakes occur. He concluded that Taipei 101 does not affect earthquakes in that area. Through this argument, what is important and what we must focus on is that Taipei 101 is prone to earthquakes and fierce winds common in its area. The engineers had to design a structure that could withstand gale winds up to 216 km per hour and the strongest earthquakes. Typically, skyscraper must be flexible in strong winds, yet remain rigid enough to prevent large sideways movement. Flexibility prevents structural damage, while resistance ensures comfort for the occupants and protection of glass, curtain walls, and other features. Most designs achieve the necessary strength by enlarging critical structural elements such as bracing. But the height of Taipei 101 combined with the demands of its environment called for additional innovations. To achieve stability and lessen the impact of violent emotion, a gigantic tuned mass damper was designed. The damper consists of a steel sphere 18 feet across and weighing 728 tons, suspended from the 92nd floor to the 87th floor. 8 steel cables form a sling to support the ball, while 8 viscous dampers and bumper systems act like shock absorbers when the sphere shifts. How was a damper so heavy able to be applied? The massive damper has weight of 728 tons, which is too heavy to be lifted with crane at once. It was divided into some prefabricated sections and welded together. The steel plates, the cradle, and bumper brackets are fabricated on site. It is then hung from thick cables and tuned to make it swing in exactly the opposite direction of the building. That was a brief explanation of the function and structure of the tuned mass damper. Now, let's go deeper for better understanding. First thing that we will go through is the basic principles of the TMDs. The main purpose of the TMDs is to act as a counteragent to observe the kinetic energy that occurs when a building moves. Let's look at this principle with a picture. Here is a virtual building with a TMD connected within. If a force works on this building, the building will sway. When the structure starts to sway, thereby generating the kinetic energy K1, the TMDs is set into motion by means of the pendulum and forces of the building to the opposite direction by the counteracting force D1. The same scenario happens when the building sways in the other direction. In summary, the main idea of a system is to match the frequencies of TMD with the inherent frequencies of the building itself. There are several types of dampers, and the tune-mass damper belongs to one of them. Knowing the type will help for better understanding. Although Taipei 101's website introduces it as a passive damper, it is actually closer to a hybrid damper, a mixture of passive damper and active damper. Passive damper and active damper are classified according to how they respond to and manage vibration. Passive damper responds passively to vibration using simple mechanical devices, fluids, or elastic materials, while active damper actively responds to vibration using a closed-loop system with feedback. Hybrid damper can work either as an active damper or a passive damper, according to the loading. Let's take a look at the actual structure of how active and passive damper coexist in Taipei 101. The cables connected to the mass block and the mass block act as a passive damper, such as a pendulum. Below it are 8 hydraulic viscous dampers and bumper systems. The hydraulic damper is a device that, in short, converts the kinetic energy generated when a structure moves into heat and then releases it into the air. Compact but powerful, these dampers increase structural damping levels to as much as 50% of critical. The result being a truly dramatic reduction in stress and deflection. The damper of Taipei 101 has 8 hydraulic dampers connected under a steel ball, which affects the reduction of vibrations in buildings. There are also 8 snubber viscous dampers in the bumper system, which usually do not affect the reduction of vibration, but prevent the steel ball from failing out of range in the event of a major tremor, such as a typhoon that comes about once a century. These too serve as active dampers. As a result, there are 3 advantages. First, there is less risk of instability than active damper. As soon as the structure detects events that can cause the active damper scheme to fail, the system can switch to manual TMD. Second, because the actuator is not used continuously, it costs less and reduces energy costs than the active damper scheme. Third, since hybrid damper can apply a force, they still have a way to vary the range of frequencies for which they are efficient. In terms of performance, the TMDs have moved up to 35 centimeters during high winds and is designed to be able to move up to 150 during extreme typhoons. It cuts building vibrations by 40%. In addition to this wind damper, Taipei 101 also uses 2 smaller dampers, 6 metric tons each, on its pinnacle to reduce vibrations by another 40%. Dampers have also been placed on elevators in the building to increase their stability. We spent time mostly getting to know about the TMDs. As the lateral forces like wind and earthquakes take action, TMDs move opposite to the direction of them and compensate the movement of the building. Through this, comfort for the occupants inside is guaranteed. Not only the use of the tune mass damper, but few more things are applied in Taipei 101 to overcome the seismic issue. So, for next week, we will continue on the solutions for seismic issues. Thank you for listening to our presentation.